our third video. This is where I want to teach you how to model an exponential growth situation when you have the information in a graph. So I'll talk a little bit about what it means to model from a graph and just be really clear about what we're looking for. Here I've got some data that I pulled off the internet, and it is the world population. Now, I will put the link in the in with this video because I'd like you to take a look at this website. It's really pretty neat. You can actually set the limits by sliding these sliders to say where you want to start and finish the data. But what you'll notice is that when you slide this, no matter where you slide it, what you're going to see is this sort of curve that has this characteristic exponential growth. So what we're trying to do when we say, hey, we want to model this exponential growth is we're really talking about trying to find a rule so that we can understand how to predict if this trend continues. And let's say we were missing data in between, we would be able to use our rule, our equation, to fill in any missing pieces for which we don't have data. So that brings me to my first sort of really important point, which is that what we've got when we see data on a graph is typically data that we've gotten from measurements. This is the real information that we measured. So this was the real population. We found out how many people there were, we counted them, and we graphed that data. Now, when we've got data, what we've got is real information. Okay, this is what we really measured. But the problem is when we just take measurements, we don't have a rule. So what a model helps us to do is to write a rule that allows us to predict. So the data is what we actually measure. The model is the equation and maybe the graph of that equation so that we can see it that helps us to predict. Now, when we see data, the first thing that we might notice is trends. That's the part where we go, oh, this looks exponential. That's what helps us to understand what kind of an equation we write. So then we take the model and it shows that trend, assuming that that trend will continue the same way. So we look at this and we go, this looks like it might be exponential. If we assume that the growth is going to continue to be exponential, the rule that we write for that will help us to predict. Now, the data is true. It's just a reflection of what we measured, but it might not be exactly nice and clean and be exactly exponential. And we saw that when we looked at the Skittles example when I showed you how to do this with a table. The model is likely not going to be 100% accurate, but it does allow us to make good predictions. So that's the value of a model. A model helps us to make predictions. It's not necessarily 100% accurate. It might be off by a little bit, but it allows us to make predictions. The data is the measurements that we took. Now, our goal when we're trying to model a situation is not to be perfect. What we're going to try to do is we're going to try to model that data, and we're just going to try to hit a couple of points. So what I did first is I took 2 data points. I went to the website and I put a little point on here, and up here in the top corner it actually told me exactly what that point was. So I took 2 points and I just put them on a graph. First thing that I did, I went into Desmos and I said, well, I'm gonna put in those points. So in 1804, the world population was 1 billion. Now I want to show you this, and my picture's kind of covering it up here. 1 billion is this number, 1 with 9 zeros. Now, when we're working with really, really big numbers, it's oftentimes really more convenient to use scientific notation. So we know about scientific notation. This is 1 times 10 to the 9th power. We've covered that earlier in this year, and this is going to make our math a little bit easier to write about in this problem. So we're going to use this 1 times 10 to the 9th, that's 1 billion. So every time we see this 10 to the ninth. We're really talking about billion people. So I've got my graph here, and I've graphed 4,1 billion. So what I'm saying is 4 years after the year 1800, that's where I'm going to start my graph, just to make it small enough to take a look at. We're going to look at what's the population growth from 1800, the year 1800, up until now. Okay, so the second data point that I found from the website was here in 1999. It was 6 billion. So again, I put that point 199. That's 199 years after 1800. That's 1999. It was 6 billion. And so you can see there's that red point and this blue point. And I had to zoom out so that I could get this graph to look nice, and so that I could see my data points here, so that I could really see my graph. So what we're hoping to do here is we're hoping to get an equation that allows us to draw a curve that goes through these two data points that I have. We're hoping to write an equation. When we say, hey, we want you to get a model for that graph, what we're basically trying to do is we're going to try to write an equation, and that equation is going to look like, y equals a times b to the x, because we're thinking it's exponential. And when we graph that curve, we're hoping it's going to look like that exponential and hopefully hit close to those data points. Now we know this point at 1800, that's going to be our starting point. That's going to be our A. And we're not exactly sure what that is. I'm going to show you how to do that algebraically. So we're going to start with those two data points that we have. In 1804, which was 4 years after 1800, we had 1 billion people. In 1999, so that's 199 years after 1800, we've got 6 billion people. And so I just wrote that information right here. Now, we know that the equation that we want to write is going to look like this. Y equals a times b to the x, or in function notation, f of x equals a times b to the x. So that's what I've written here. When I put 4 in for the x, that's 4 years after 1800, I should get a population of 1 billion. So that's what this setup is. And similarly, for the year 1999, 199 years, it's 6 billion. Now, when I have these two equations, I have a handy little thing here. Both of these have my starting point in them. And that starting point's the same starting point. It's the starting point we're looking for. It's this starting point. That's what I'm looking for. So if I can find out what that number, well, it's going to be the same number that models the 4th year. It's going to be the same model that models the 199th year. So this starting point is going to be the same A number. So what I'm going to do is I'm going to say, I'm going to solve for this A. So I've got A times B to the 4th equals 1 billion. So if I divide out that B to the 4th, both sides, right? B to the 4th, then what I get here is that A is 1 billion over B to the 4th. Now, I'm not done yet, but now I have one way to write that starting point. Now, over here in the 1999, I can do the same thing. Again, I'm going to divide out this B to the 199. So I'm going to get that the starting point is 6 times 10 to the 9th, 6 billion people, divided by B to the 199. Now, both of those are A. So what I've got here is 1 times 10 to the 9th, that 1 billion over B to the 4th is equal to 6 billion over B to that 199th. Now, immediately I'm looking at this and I'm saying, well, look, I've got this 10 to the ninth on both sides. Why don't I divide both sides by that 10 to the ninth? And that's just going to basically have the effect of canceling this out, canceling out these billions. I'm just basically simplifying my math here. Let me write what that looks like. So now I've got 1 over b to the fourth equals 6 over b to the 199. Well, now if I do cross multiplication, now I've got 1 times 10 to the 199. I'm sorry, 1 times b to the 199 equals 6 times b to the fourth. So now I'm going to do a little trick here. I'm going to try to find out what b is. So I'm going to divide this b to the fourth off of both sides. I'm going to divide this b to the fourth and divide this b to the fourth. So now I've got over here, this cancels out. I just have 6. Over here, well, multiplying by 1 doesn't change anything. What I've got here is b to the 199 over b to the fourth. Well, we know how to deal with this. We know that we have these rules of exponents that says if I'm dividing with exponents, well then this is keep the base, subtract the exponents. So this whole thing, this whole fraction here, this is b to the 195 equals 6. Okay, well now we have to use one of the last things that I taught you before we went on spring break, which is if I want to solve this, I can raise both sides of this equation to the reciprocal of this exponent. In other words, 1 over 195. 1 over 195. So that's going to get this b by itself. And I've got this is 6 to the 1 over 195. Now, if you type that in your calculator, you got to be careful here. You might want to put that in parentheses when you're up there in that exponent. But what you end up getting when you type it into your calculator is you get this b is equal to 1.0, let's see here, where is it? 1.0092. 1.0092. So what this number is basically telling me is that the population is growing by not 10% and not 1%, but 0.9% every year. So just really close to 1% per year. This tells me that my population, this is my scale factor for my exponential. That's this b number. That number tells me I'm going to be growing by just a little bit less than 1% every year, my population. Now, the last step that we've got to do is we still have to find out what our starting point is. But now that we know what our scale factor is, we can go back to one of our original equations. I'm going to use this one because the numbers are a little bit smaller and say, well, okay, well, it was a times b to the fourth equals 1 million. But wait a second, I know what this b is. I don't need to put a variable in there anymore. I know that b. That b is this 1.0092. Make some room there. 0092 to the fourth power, because it's the fourth year, equals 1 million. So now I divide both sides by this 1.092 to the fourth power. And again, I'm really glad I have a calculator because I don't have to do all that calculating in my head, and the calculator can do it for me. And when I put this into the calculator, what it tells me is my starting point, and I've already done this calculation, so I have it written down here. My starting point is this number, 964. 964, 031, 073. So what this is telling me is in my starting year, which was 1800, my starting point was about 964 million. 964 million, that's what this number is. So that tells me what my starting point is, and it tells me what my growth rate is. And so now what I have is a model that works. I have this model equation. This is my model equation. It tells me my starting point, this is my A, is this 964 million-ish number that we had in the year 1800. And this tells me my B, which is basically 100% plus about 1%. This is 0.9%. Not quite 1% per year. That's my growth rate. So this is my A times B. This is my B to the X. Tells me my population is growing by about 1% per year. And when I actually type that into Desmos, it tells me that it's a pretty good model. And one of the things that I want you to understand is, how do we know when it's a pretty good model? Well, one thing I notice is that when I put that equation in, first of all, it hits my two data points that I was aiming at. So it certainly is a good model for those two data points. It certainly seems to show that exponential growth trend. And what I noticed is that it makes pretty good predictions. When I just read the year 2040 on the graph, of course, I don't know what the population is going to be. We haven't gotten to the year 2040. But my trend, my model seems to tell me that it's going to probably be around 9 billion. That's the model that I wrote for this. Well, then I went back to that website that had the model, and sure enough, their model that was on the website said they're predicting that it's around 9 billion as well. And so, this model I can say is a good model because it gets really close to the data points. That's the first thing. And second thing is that it makes good predictions. So that's how we model a graph using an exponential equation.